two variable function going into one variable. So you know what kind of input is, what kind of output is, right? So this will be usually, last time we looked at energy, like heat energy function and things like that. So and then I introduce it like this. There is a, heat energy level 2, or whatever the energy they represent, or you could simply just level curve if you don't like physics. And all right, it turns out there's a dramatic difference between these two different levels. It's 2 in 1. So here it's changing, from high temperatures to low heat energy. So I think there's this vector indicating that there will be flows like this from the higher heat energy level to the lower energy level, right? But if you look at it here, it's the same thing. The heat level is 2, but 1 is down there, so the direction is going to be a little bit of that direction. Why is the other one longer than the other one? Right, it's a gradient. Why is the gradient here supposed to be longer than this one? Gradient is the opposite. Actually, the gradient is going toward to higher level. So that would be the vector field you obtain by gradient of this one minus, right? Opposite, completely opposite direction. So if you look at each of this point and knowing that there's picture behind it, there's this level and this one is supposed to be bigger. It's because the distance from here to there, kind of level difference, is long. It's very slow change, right? But here, level 1 is right next to it, right? So the change is a lot faster. So this is representing the velocity of changes of these heat energy. So that's what this derivative is representing, rate of change of these things, level curves, correct? So that's what this is representing. So this is the idea of the vector field. Especially this vector field generated from this process is called what kind of vector field? Because it's this algebraic shape, it's a gradient vector field. Gradient itself in the vector field. All right? So it's naturally understood from that energy level and things like that. But there are other, so this, I'm not going to go into how we're going to interpret this one as a force vector field, but whatever that meaning of these vectors are in physics is a vector field. But probably the very first vector field where you were exposed is the universal gravitation vectors. So maybe there is some sort of dark matter we don't see, you can't really understand, but if you look around, there is this force field around it. Here's a force field and here's a force field. Seems like if you put something in there, and there will be this force created, right? But if you're closer here, seems like stronger forces created, things like that. So we don't understand any of this energy level. If you look at, this is how Newton at the beginning understood force vector field around this gravitational force, right? So that's a vector field without phi existence. It's a vector field. It's a gravitational vector field, which we call F. And in this two-dimensional world, we can put P and Q. Is this notation again in PQ? If I choose one point x comma y here, and this P and Q are functions like the two-variable real function. So if you plug in this x and y in there, then it's going to tell us what the vector is. So it turns out it looks like this. So I better use this example. Negative kx, k is a constant, the root x squared plus y squared to the third, negative ky, root x squared, y squared to the third. This is called universal gravitation, law of universal gravitation, discovered by Isaac Newton. This is description. If you choose x comma y, then its direction and its magnitude of the force field looks like this. There's some constant, whatever that mass is involved. Okay? So that's a vector field. The natural question is that, together with this one, is there some sort of energy function? We don't know. Energy function such that this one is phi x and phi y. What is the name of this vector field? Phi x, phi y. What's that? Gradient vector field. Phi, existence of some sort of phi from two variable real function, two variable to one variable, just like this heat energy. Can there be some sort of abstract notion of this energy so we can imitate what happened to the heat flow? Is it possible? That's a question. So what is the question? The vector field, a universal gravitation vector field, is that the gradient vector field of some sort, right? Some reason they describe it differently. Is this term conservative vector field? That's the term. Is this a gravitational force field? Is this conservative? That means there's some sort of mysterious function, phi, real valued function, such that that force field is realized as a what? Gradient vector field. Different terminology. I think historically they thought of it in different contexts. So we have a conservative vector field, right? So the answer is yes. It turns out that phi is what is this? I think it's a k divided by root x squared. That's it. And k divided by that's it. It's supposed to be one variable function, right? I mean, real valued function, so it's not a vector at the end. Here, like that. Sorry about that. So that's a k divided by root x squared plus y squared. Okay? Even negative. Put in there. Whatever that one is, so mathematically try to make that effort. We have this one from Isaac Newton. We're going to find this one out. So we're going to integrate with respect to x. We're going to integrate with respect to y. See if that's kind of matched together. You can imagine it's not very difficult to, came about here. So they realize, yes, there is this two variable real function. Everything is nicely defined except that x equals 0 and y equals 0. So if its gradient vector field is this one, right? So they realize this mathematical paradigm is a better information, than this force field, because this force field is going to come out through the unique operation we do to this function, to variable function. So this is kind of packing that information to a more compact and more beautiful and symmetric form, right? In all the physics, when they're talking about the symmetry and symmetry, is one idea. Packing a more complicated information, more compact form, and everything else is just derived as you differentiate it. So this is the better information to have it. So think about this heat energy imitating the gravitation force field in Isaac Newton's description is just arrow thing and calculating that. Now it has a new interpretation. There is some sort of energy level around this source of a star, whatever, such that that it flows from a higher energy level to a lower energy level, things like that. So they decided to call this one. I don't know what to call it, but we're going to call some sort of energy, right? So potential energy. That's the potential theory is kicking in. Before it was a naive vector field. It's actually how it's moving. Behind it, this mathematical idea gives you a way of looking at it, two different things. Abstract notion is created by this mathematical idea, but it is accepted, and through the experiment, it is the right notion to think about. Potential energy is created by this one. So you pick one point there, and this will tell you something, some number, that energy level created by the gravitational force field. All right. So, this is a big question, but in general, it is not always so. If you have some sort of vector field, it's not always a gradient vector field. Okay? So that's where we're heading. So we have, let me look at the note. So big question that people ask is that if we have a vector field, PQ, so that's a vector field, given, is it conservative? And you can write down arbitrary vector field that it is not conservative. Okay. Does anybody know how to check if it is not conservative? Check it as a conservative. If it is a conservative, it must look like this, right? Not knowing what phi of x and phi of y are, There's a quick way to check using the Clairaut's theorem. Remember that? If you do something to that and something to that is supposed to be the same, if it is partials of the same function, what's the Clairaut's theorem says? Phi xy is equal to phi yx, right? So whatever you're looking at P and Q, if you differentiate this one with respect to y, if you differentiate that one with respect to x, they're supposed to be the same. If it is conservative, right? So a quick answer here is not a partial answer. It's not a complete answer. Partial answer to that question. If P y, does that make sense? Why I'm differentiating this one with respect to y? Mine is if minus Q with respect to x. If this is not equal to 0, then what's the conclusion? Not conservative. If it is conservative, they're supposed to be the same, right? Not conservative. But don't use that. If it is equal to 0, then it's a conservative. You can't argue that, right? You're a math major. You should know better. This itself doesn't imply that. But there is some connection. Nice connection. This is a good indicator. Have you seen this one recently? In some theorem? What was that? Green's theorem? Right? Is this inside the Green's theorem, right? Yeah, inside the Green's theorem. That's right. All right. So that's one question. So now that's the side, and then integration. So let's look at the integral side, integration. Yet there's no complex number. It's just a two-variable real-valued function. So let's think about integrals. Where is this integral is considered in physics is work calculation and flux calculation. This really makes the gist, the brief description of how the integration is used in physics. All right. First, you start with the work calculation. Flux calculation is a little bit more involved, but it's kind of the same idea. So I think we'll just stick to the work calculation all the way to the end of the semester. I don't think there's any flux calculation kick in, but flux calculation is very, very important. Lots of ideas in relative geometry, general relativity uses this idea of integration to measure and formulate ideas. But work calculation. So here is, for a start, here is really strong rod. So there's no sagging at all in gravitational field. But there is this ball has a hole in it so you can move around. Okay? But this is a gravitational field, so as soon as you put that mess in there, gravitational force is created like this, downwards. Now you grab this one and move this one over here from one end to the other end, and you did some work, right? Your arm, your muscle did some work, and gravity is acting on it. So gravity is doing some work, right? So two things, my arm and gravity are contributing to this work one way or another. But if you think about how much the gravity is helping moving me go from here to there, is a 0. And usually it's calculated, what is the component of this gravitational force along the direction of our motion? It's a 0 because it's perpendicular, right? So in that case, it's a 0. But if you have some straight upward like this, the rod is now slanted. Now we have a ball here and have a hole, and we're moving this one up there, and my arm is definitely doing more work than probably this one, right? Moving up there. And how is this gravity is contributing in the middle of the way here? How is it contributing to that? It is actually pulling it down somewhat, right? You feel something, then it's perfectly horizontal. So it's working against it. Your muscle is really dealing with something coming from gravity, which is acting against it. It's pulling to that direction, right? This is called the scalar projection. Now, at that stage, there's a constant gravitational force, and we have this is unit vector along the direction of that at that moment, and you multiply by, this is the component of the force coming from gravity, right? So do you think it's going to be positive or negative? This is the unit vector direction there. Gravity is pulling backward. It's going to be negative, right? If you do the scalar projection of this going up and pulling it down, you will get a negative number. Multiply by how much you're moving that, delta S. This is work calculation. How much of the force is applied to how long, right? Okay. So that one, if you do the older Riemann sum, that will be the calculation of the sum. If you're going down like this, it's kind of odd experiment, but you have to separate what your arm is doing versus what the gravity is doing. If you don't even touch that, then gravity is going to pull it down. You can see with no friction, it's going to pull it down. The gravity is doing the actually work of moving this one to that. But if you grab that and pulling it down, your arm is also doing the work. So you separate it. How much of the work is coming from the gravity versus what your arm is doing. So if the question is that what is the work done by the gravity going from here to there, is a positive number. It's helping. And here, if this one is going from here to there, how much is the work done by the gravity? It's a negative number. It's not helping. Things like that, right? So that's the idea of the work calculation. If it is a sag like this, it's really a cable car going from here, the cable car going from there. Now you can see that direction is all changing there, right? It's just normal. It's the same thing. Constant gravitational vector multiplied by the direction of the normal vector there, unit vector, which is constantly changing, multiplied by the short line segment there, right? Now this one will be different. At every moment, this direction is changing. So we use parametrization. Miraculously, I'm not going to go through it in detail. Miraculously, this is approximately same as this force vector field times the derivative of that parametrization times delta t. Okay? So how many parametrization is there from here to there? If you look at this curve, how many ways there is to parameterize? There are infinitely many ways to parameterize. If you have one parameterization, you can change that t to the t cubed, t to the fifth, t squared. It's still parameterization, right? Think about the parameterization of a circle. Cosine t sine t, right? How about cosine 2t sine 2t? It still goes through the same circle. It's just going faster, right? So don't think that this RT is parameterizing the actual motion of this thing. It has nothing to do with that. It's any parameterization. Miraculously, these two things are still the same. This is called parameterization independence. This work calculation turns out to be, doesn't matter however parameterize your path, the work calculation is going to be the same. So this one is, if your parameter t equals a starts here, ends it there, and whatever that calculation we're summing up, force vector field, dr dt, that if you just calculate this complicated thing, it's dot product is a scalar anyway, right? In terms of t. dt, this is calc 1, actually. What's in here is one variable thing. Everything is parameterized. Okay? This one is measuring this work. And I'm saying this is a parameterization independent. Doesn't matter how you parameterize this one, this is going to be the same. But it's an orientation dependent. Your parameterization should start in here and end up at there. You can't parameterize it starting from here to there. You get an opposite direction, negative number. Parameterization independence, but orientation dependent. Okay? That's the nature of this integration of vector field. Right? Integration of a vector field, arbitrary vector field. So because of the parameterization independence, they decide to write it like this parameterization independent notation. This curve is called C. The curve itself, the path, not the parameterization. You put the curve down there, and the vector field right here. And I think it's a good notation. It reflects what happened as you parameterize. So we're losing all the parameterization part dt and only have this differential dr. And you see this notation a lot in the higher mathematics and geometry. It's called differential. It doesn't have d something in the denominator. Whenever that happens, how do you understand this notation? Parameterization free. Doesn't matter what t and you parameterize, put it in there, the result will be the same. Hence, they use this abbreviated notation. Just the path, the curve itself, and vector field itself, with whatever parameterization you put in there, it'll be always the same number. Okay? If you do a little bit of vector analysis, it's do that. That's a Calc 3 part. So that is, what is the definition of this one? Line integral of a vector field. Line integral of a vector field. Okay? Fundamental theorem of line integrals. That was homework. I asked you to review this again, right? All right, what was that? Line integral of a vector field, right? So that's in general the meaning of the vector field. But what is this? This fundamental theorem of line integral is about special vector field. What was that? So I'm going to sketch a curve here first. I have some curve starting here, there, and we have orientation, right? At least you got to have this orientation. A to B, that's 2 points. Then we have a vector field, right? So it's about integral of that path C with at least orientation, not necessarily parameterization. Then what this fundamental theorem is about? If the vector field is gradient vector field, right? Gradient vector field like this, then this notation. Now you use a parameterization. Okay? Then what happens? Right, vector field at an endpoint minus vector field in the beginning point, right? That's the fundamental theorem of line integral. Well, it's simple. It just looks like a fundamental theorem of calculus. But the significance of this one is the following. This only cares about beginning and end, right? I'm going to sketch it in a slightly different curve. Maybe I'm going to go around like this. This orientation, I'm going to call that C prime, right? Now you put that C prime down there. What's going to happen to the result? Yeah, you just started and ending it is the same thing, right? So if you integrate along this one or along that one, you end up at exactly the same. So this is called path independence. Okay? So what kind of the physics example have we seen is a gradient vector field earlier. This vector field turns out to be gradient, historically important one. Gravitational vector field, right? Gravitational vector field is what? Conservative here. This vector field is the gradient of that scalar function, right? So if you're moving something to here to there, if we have the gravitational vector field, the change of the work done by this thing, in here, right? This is calculating the work, remember? Work done by the gravity from here to there is a difference of what? Phi. What was the name of a phi? Potential energy over gravitational vector field. Whatever that abstract notion is. There, if you're far away from the star, we have a certain potential energy. If you're closer to the star, we have a certain potential energy. This energy flow is exactly the gravitational vector field. So it is saying that work done by a gravity of going from here to there is a difference of a potential energy, not about how you're moving things around. And you learn that in physics, right? That phenomenon is mathematically formulated like this. All right, there's a parametrization independence, there's an orientation dependence, and thirdly, path independence, right? So that's a review of these line integrals in the real values. All right, so that's great. It has this path independence property. And I'm going to describe, typically this path independence property is described like this. C, and they put this little circle around it, and gradient vector field dr is a 0. What that indicates is that it is not just curve going from A to B. This is a curve starts in here and coming back in there. This is called closed curve. If you're doing the line integral to the closed curve, then this is denoted like this, line integral with a closed curve like that. All right? But its definition is really the same thing going on here. Again, it's an orientation dependence and all that. And what happens is that this path independence is equivalent to this integration over the closed curve being 0. That's a nicer description. These two things are equivalent. Of course, if you look at here, if you start and ending up at the same, phi b minus phi a equals 0. So that part's easy, right? And going backward is constructed by, okay, if I started here and coming back and here again, this can be done if you have that orientation. Just choose one point in here, C, and divide this curve into two pieces. And then if you apply this one 2 times to that, and it turns out you get this one. So let's just skip that part. This is usually explained in Calc 3. This path independence, fundamental line theorem of line integral in this formulation is equivalent to this one. All right? The closed curve integral is being 0. All right. So all the gradient vector field has this property. The conservative vector field has this property. So the next question is that if we have a vector field like this, such that we don't know if this is conservative or not, we don't know if it is gradient vector field or not, but we realized whatever closed curve integral you do, line integral f dr, I really like to write it like this, so I want to get used to this. PQ, that's the vector form, right? Column vector form times dr. The same notation is 0 for all closed curve. Since this indicates a closed curve, I'm going to write it like this. Suppose this is happening in a little region. Then what is the question we should ask? According to what happened in here. What happened in here? If it's gradient vector field, it has that amazing property, right? Now, if you are staring at this property and you want to ask if f is gradient vector field, right? That's what we want to ask. Is there some potential function exist from 2 variable real function to 1 variable such that that gradient vector field we're looking at, just like gravitational gradient vector field, is the gradient of phi, right? That's the question we like to ask. Is this true? Question make sense? We have gradient vector field had this amazing property. Is this property determines this is a gradient vector field? The answer here, since I made a mistake and there's a fix for this one, so the question is that if this path independence property will translate directly to this conservative vector field, the answer is yes, and especially this answers on any type of region, in particular whether it has a hole in it or not. If it is completely filled in, is simply connected or not. This, if the path independence property will give you a conservative vector field condition. So again, it is about constructing. This one is a construction. It's straightforward. If I have some arbitrary, let's suppose we have lots of obstacles there, so there's this holes, and this is the this is the thing, and we have vector field has this path independence property. So what is the definition of this potential function? This potential function is defined like this. First, you go and fix one base point that never moves, so that's our base point, and our target point x comma y is somewhere here, for example, like that, x comma y, and we're going to use a path because this is supposed to be a connected piece. You can go around things like that. So that's our path gamma. So we're going to do this path integral starting from here and ending it there. And you do this integral of the vector field. So there are many different ways to go starting here to ending it there. You can, slightly more bend around or take a completely different path around this singularity and it holds and around there. There are all the different ways. But as long as you start and end up at the same point, and this path independence property will give you always a common number. So it doesn't matter which path you choose. So because of that strong property, this turns out to be well-defined function. So if you define it like this, with that definition, you have the property that locally this derivative, the gradient vector of this thing, matches exactly that thing. So here the answer is this path independence property is equivalent to being a gradient vector field, conservative vector field. Redo in here, conservative vector field on any type of region, and that's the strength of it. So I realized I didn't really answer about the other condition. So here's path independence as another strong property that is actually equivalent to the conservative vector field. But there's another thing that was attached to this conservative vector field was that curl calculation. So if you have a conservative vector field, PQ, then we know that it's QX minus PY, that curl is supposed to be 0. And then we're asking the backward question. In general, it's not true, but there's a better answer than this just in general is not true. So that's what I'm about to do in here. This is a very local condition. So from that much of information, not having this path independence definition, if you look at here, is very, very strong. Have this any path around here to get there, and then we have this integral value as a function value. But if you have this local condition in here, and to build up from here to this potential function, you go through integrals in that effort of going from this local condition to constructing a potential function involves integrals around rectangles. So because it involves a partial integration, you integrate along the x-axis first and along the y-axis later and things like that. That requires, for example, if you started here in a point A and you want to go to an x comma y, that requires kind of a little bit of a neighborhood around it here. So anywhere you put in a point in here, if you integrate along the x-axis, and you must be able to integrate along that, any point in here you should be able to integrate along the vertically. If that's always allowed anywhere in the region, for example, like a simply connected region, you can always find inside being completely defined and there's no singularity for the vector field. If that's the case, this integration is possible to get to the final construction of this potential function in phi. But if there's an obstacle like this, when you're integrating this one along the axis and along the y-axis, this construction will eventually fail. In worst cases like this, for example, if you have, you can have regions like this, kind of rectangular region, but you only have this type of region like this. So using that iterated integral along the x-axis and along the y-axis, you can construct phi on that rectangular region. Okay, and you can, if you have that, and you can continue constructing along that region there all the way to that. If you have that much, you can go continue that integration vertically like this down in here, and then you try to complete it here. But this is already done, and this part's done, that part's done, and there's no guarantee that when you're coming back to this continuing the construction, when you patch these together, what happens between these two boundaries is really is differ by example by example. There are some examples, although there's a singularity in here, so you have to avoid this rectangular construction using this iterated integral along the x-axis and y-axis. If you go around like this, eventually when you come around here, lucky enough, that'll patch it perfectly together. But this continuation sometimes leads you to some gap in here so that you can't close it up. Okay, so you can only do the construction of this sort, leaving the last boundary incomplete. So if you look at this pattern here, this is again kind of simply connected region, so it's already covered. An earlier theories, a local construction will allow you to construct this potential function for local region, and it's actually can be extended to any simply connected region by keep constructing like this. So here the answer for that one, again, to summarize it, if you have this curl zero condition, we can only construct to this potential function on a simply connected region. You can accomplish that much. But if the domain itself is not simply connected like that, and this construction, and there's no guarantee that when you kind of go around and try to close up, and there's no guarantee that it's going to patch together perfectly. Here the complex in here. Complex integration. This is not mathematically absolutely correct introduction, but there is no logical gap. It is just limited, and that's going to be good enough for this course, and especially is good enough for you to understand the meaning of the complex integral, why we even care about this one. In that way, I think it's a good motivation. And book has nice first page rigorous definition, Riemann sum-like definition, if you like, and that we're not going to do. But those who are going to take advanced calculus later on in your education here at Armstrong, you will get into that Riemann sum, and it's pretty boring. But it has something you have to go through, understand the foundation of in the logic in mathematics. All right, so here we start with a complex analytic function, u plus iv. All right, I plan to go over how significant this thing is in the area of the modern mathematics. That I'll skip in here, but we'll just enter something right into that. So I forgot to actually mention the Green theorem in detail, but so let me see this all together. All right. So we have the Green's theorem. It's a real important motivation. What does Green theorem says? In its hypothesis, there is some long paragraph you might have neglected, but that's the important part. So they call some curve here, which is not just closed. Anybody remember what it says? It's not just closed. There's a word that is a simply closed curve. Closed means you start and end at the same thing. Simply means there is no crossing itself. It's Jordan curve theorem, which the book clearly states that. It's a fancy theorem, and it's very difficult to prove. Again, you see that in only an advanced calculus level. The two fact creates inside region, outside region. Of course, if I draw a simple thing like this, everybody understand simple means no crossing like this, closed means start and ending up at the same. But you can imagine really complicated shape, right? And Jordan curve theorem, that too says that two condition actually creates inside region and outside region. Divide this entire plane like that. So we decided to call that inside region D, and this boundary of the curve, the region, created this standard notation, boundary notation like this. It's not partial. It's a standard notation for boundary, like a partial symbol. Make sense? Region, versus the boundary of the region. Okay? It's a simply connected boundary region, so I don't think we have questioned much about boundary region. So that's the hypothesis. One more hypothesis is that we're looking at this curve and we're about to enter integral of a vector field, line integral of a vector field, right? Line integral of a vector field is what independence? Parametrization independence, right? But what dependence? Orientation dependence. So you got to give this orientation when you enter. Orientation is called positive orientation. So either you go around that thing this way or the other way around. And they're saying when you're going to positive, going in that direction, if that interior region is on your left, then it's called a positively oriented. If you're going the other way around, you can see the interior region of this is to your right. That's negatively oriented. But we positively oriented like this. Only difference is a plus or minus. Now, the Green's theorem says positively oriented boundary, and we do the vector field, the P, Q, dr. What is this? Line integral of a vector field, right? Parametrization independence, orientation dependence, right? But often books write it like this. There's this oriented curve. P is multiplied by dx. And Q is multiplied by dy. Because R is your parameterization of a curve, and it has x and y as a position. And dr dt is, of course, dx dt, dy dt, right? That will be the velocity vector of your parameterization, correct? Yeah. So dx is there and dy is there. This dr dt would be this one, but they're not putting dt in there because it doesn't matter how your parameterization works. It's all you care about, this dx dy, where is it multiplied. Make sense? So they use that notation. So that part is not Green's theorem, but Green's theorem is what? It changes to double integral, right, of that region. And what goes in there? Q appears in the front, P appears in later, px minus py dA. This is double integral, not iterated integral, double integral. All right? So this is supposed to be volume, remember? Double integral of some function is a volume curve under that. So that's the meaning of the theorem. All right, this one is a simple version of a curl. Remember curl? Curl is a phenomenon that is happening putting a line integral into, what is this called? Surface integral, double integral. If it is a three-dimensional and it gets really complicated, you remember the curl formula is pretty complicated. But if it's two-dimensional like this, curl formula is really simple. So this is really curl. So that is called the Green's theorem. Okay? So I'm going to show you next phenomenon here. So we are in the context of complex integration, and we have this u and v, and you're staring at the end qx minus py. Complex function u and v, and the partial derivative x and partial derivative y. Any connection that comes to your mind? Right now it's Green's theorem, there's no complex, and then here's the connection that we're making in there. Pretend a connection, you're going to discover this one yourself. Qx minus py, and I have one, the real part of the complex number and imaginary part of the complex number. What comes to your mind? We have two real values function. U is just like this p, right? There are two real input, one real output, right? That's what u is, right? Real part. And v. And here we're talking about some sort of partial derivative minus, right? CRE doesn't come to mind? CRE? So what condition do we have? So that one, in my scenario, is supposed to trigger you, CRE, but it didn't, but it's okay. CRE. All right, CRE is about u and v, right? So let's do this u and v. So ux minus vy. Fair enough? What do you know about this guy? Ux minus vy. It's a 0. It's going to be 0, and then it's going to give you a nice result. All right, so let's trace it back. Now we start with a 0 because of whatever little integral, little region do. So we're doing this one locally. Do you know why I'm this locally? Can somebody explain why I can only do the following processes locally? I'm about to use Green's theorem. What is the hypothesis in Green's theorem? Simply closed, right? Everything inside must be okay, right? Inside it should be okay. That can only happen locally. If you look at big picture, maybe there is a giant hole where the u and v are not defined. So only locally we can do this one. And d, what are we doing? Ux minus vy, is that right? Correct? Then it's going to be 0. Green's theorem says it's actually what? Positively oriented boundary line integral of what kind of vector field? So when you enter the Green's theorem, you swap this thing, right? So that's all you have to do. Swap it back. V goes in there, right? This was a Q and P, so swap it back. And then V goes in there, dx plus U goes into dy, right? And that's going to be 0. So that's going to be the vector field. V up there, x pod, U down there, and dr. And that's going to be 0. Locally, doesn't matter which loop you choose, any crazy loop you choose, if it is even self-crossing, then you can divide it into one piece by piece, and then you can conclude that this is always a 0. So what is this property called? A 0 equals that for arbitrary boundary D. What property is that I named? This is arbitrary, right? Because this is always 0. No matter what region you put, it's going to be always 0. So the boundary is arbitrary. Or whatever you put it in there is going to be 0. What property is that? What's that? Path independence property. Path independence property. So we're looking at a vector field VU, kind of swapped around, is path independence. If you know the path independence, locally, what conclusion do we have? The whole half of the class of a discussion is about some sort of vector field, right? Conservative, gradient vector field. So going back, turns out this VU is gradient vector of something, phi. Locally, globally. Only locally, because Green's theorem requires that all things are in there. All right, let's do one more thing. So, well, that's not the only CRE we have, right? What is the other CRE we have? Got to put x first. It is Vx, right? Vx plus, because it's opposite sign. What do you think? Uy, there was negative, equals negative uy, so it's a plus. Now this one is 0. Is that right? Okay. Now we're going to swap, and then I'll end. Now we're entering line integral with a positive orientation. We're going to swap it, but it requires this negative, right? Remember, Green's theorem has a negative symbol in there. No problem. You just put that negative in front of ui, so you go back there with a negative. Is that all right? That when you're going back to the negative, negative becomes a positive. So that's dx. Plus v is just coming in here and dy. That is the this vector field, negative uv dr. But if you pull out negative, which is allowed in the integral, turns out it tells us the secret better. So we have to pull out another, what is it? Another path independence property. Is that right? Well, this vector field here we're looking at also have path independence, right? So we have two vector fields with a path independence. Okay? All right.